Well, with that being said, so this track is top 10 low-cost ways you can save energy in your building. Jane Dyer here is presenting this topic today. Jane is registered professional engineer in 2 states and started with ETC Group in 2007. Jane is responsible for energy analysis, cost and savings analysis, audits, field work, and implementation for energy savings projects. She has worked extensively in the healthcare, higher education, and entertainment sectors. She has delivered this presentation on numerous occasions, including the Global 2013 Energy Symposium, Association of Energy Engineers Reno and Las Vegas chapters, and the Project Skyline Education Series. So with that, let's welcome Jane.
Are we working? Thank you. So I assume everybody was here this morning for David Orr. Is everybody moved? I was pretty moved. It's great to hear some of our industry leaders talk about what they're doing. It's very motivating, and to me it says, get going. We all have some part in this, and there's all something we should be doing. So I'm going to share with you what I do every day, what my company does every day, and that's energy efficiency. I don't know if you noticed, interestingly, on David Orr's list of things to do, I believe it was from President's original sustainability plan. Number 2 was energy efficiency. So I noticed that. I don't know if you all noticed that. The other thing I thought was really interesting is Wesley Schultz talked about social norms. What is the norm? Is energy efficiency the norm? And I sat there and thought, wow, yes. If we think about our community, lucky enough to have exposure to what our community is doing energy efficiency-wise, Intermountain Healthcare, BD Medical, Caesar's Palace, Paris Casino, 170 South Main, Hill Air Force Base, Primary Children's Hospital. I could go on and on about Kennecott, University of Utah, Weber State, 1/3 energy reduction at Weber State. That is phenomenal. So this is the norm. This is what the community is doing. So I'm glad that you guys came to participate in this presentation. It's pretty techy. I'm an engineer. We're all a little bit nerdy, and I'm going to share a bunch of graphs with you. And if David Orr's granddaughter with a little giraffe was here, she'd probably say that it was boring. But hang with me. I think you guys will be able to get a lot out of this and have something that you can take back to your building and implement. The idea is I really want this presentation to be actionable. I actually have homework for you when you leave, so you can take some things back to your building. Maybe there's some things you can do. Maybe there's some questions you can ask. Maybe you know the right people to go to. So with that, we're going to start off with how does a building use energy? Give me a little show of hands here. What's our audience structure? Do we have any engineers in the audience? Some engineers, architects, building operators or facility managers? Okay, any HVAC staff? Okay, awesome. So that's great. You guys are all in a position to be able to use some of these principles and apply them. So this is what we call an end-use breakdown of energy use in a building. What we're looking at here is actually a healthcare facility. I do a lot of work in healthcare. Any commercial building would look different than this. An industrial facility end-use breakdown might look different than this, but we'll use this for talking purposes. This is a building in Utah, so climate zone 5. And I was surprised when I saw this. When you think about healthcare, and you think about electric and gas use in a healthcare facility, you know, the patient care is the primary driver. And I imagined, you know, there's a lot of diagnostic equipment, there are MRIs, there's all these important things that patients are plugged into. How can I possibly do energy efficiency in a healthcare environment? And when you look at this pie breakdown, can you guys read there? What's in the orange piece of pie? Anybody read that? Yeah, interior equipment. So those are all the devices I just talked about. the MRI, everyone's PC, all of those diagnostic pieces of equipment, every admin's, anything sitting on their desk is basically in that orange piece of pie. And it's not very big. What's our big driver of energy use in a hospital or in most buildings in Utah? Heating, yeah. So the other big drivers there are fans and pumps, which most building occupants never see the fans and pumps, but those are your big piece of your energy use. And cooling and lighting. Lighting piece of pie on here is pretty little. Depending on your type of building, lighting can have a bigger impact on your overall building energy use. The other thing I want to share before I move on about systems is this breakdown is by BTU. And if you think about the right side of the piece of pie, your heating probably comes from what? Natural gas or electric? Which one? Gas, yeah. And then if you look at the left side of the piece of pie, fans and pumps, interior equipment, lights, cooling, what's that coming from? It's coming from your electric side, classically. So in the state of Utah, currently, your electric, and I kind of have it broken down on this that we can reference through the presentation, your electric use costs 3 times per BTU what your gas use costs. So in a lot of the presentation, I'll talk about how do we deal with fans and pumps? How do we deal with cooling? Because these are costing you a lot more than your heating piece of the pie. Questions, anybody? I would love for you to jump in if you have questions. I'm happy to clarify as we go, so feel free. So this is us. This is the collective us. We have a lot of ability to influence 80% of the energy use of your building. Kind of think of that 20% orange piece of pies. Those are the occupants, that's the activity of the building. But we as engineers and building operators and facility managers can really influence all of those behind the scenes pieces of equipment. So, and I'm going to tell you how to do that. So to lay some groundwork here, I'm going to draw some pictures because I'm a fan of visuals. And we all have a building, right? I'm sure it looks exactly like this. And perhaps we have a couple of floors. Does everybody's building look like that? And so, mechanical systems in the building kind of start with the air handler. At least we'll start there. So on the roof, you've got an air handling unit. Typically, could be in the basement, could be in a mechanical room. And in that air handler is a fan. So that's using electrical energy. It's already one of our big pieces of pie. And that fan is responsible for delivering air to the building through ductwork distribution. So your ductwork runs all the way through the building and distributes across each one of your floors. And in each room, this is Betty. Betty occupies this lower floor, and she's a key player in the presentation. So there's Betty. And in each room, this ductwork ends with a little control box. Is anyone familiar with the VAV box? Anybody know VAV box? Woo, yay, cool. Okay, awesome. So in this VAV box, there's a little damper, and that controls the airflow. Here's a diffuser, and this is the air coming into Betty's space. And that all is controlled by a thermostat on the wall. So this is what we call the terminal user. And this is a teeny tiny little piece of equipment. And you might be like, why is she talking about this teeny tiny piece of equipment when we're talking about big energy systems? But if you add those all up, it's all being supplied by this fan. So now we have Betty's office. We're delivering air to Betty. Another important piece, the air that's delivered to her goes back into the air handler. We call this return air. Goes back into the air handler and gets circulated again. But very importantly, there's a set of dampers on your air handler that brings in outside air. So we are the HVAC industry, right? And everybody knows that the ignored piece of that acronym is the V. So ventilation is an important part of energy use in a building. So ventilation to the building comes in through the outside air dampers in this air handler. So now we have air going into the building. We're circulating the air. We have the ventilation piece. What about keeping Betty cool? So potentially in your building or potentially as a standalone building. I actually just drove by Weber State's chill water plant this morning, lost trying to find this building. So potentially in another building on your campus, you've got a chill water plant, and it's blue. This marker's not very good. So you've got a chiller. This is what's making cold water. And the cold water is being pumped to this air handling unit. There's a coil in the air handling unit, and then it's got a control valve so that we can say, yes, I need cooling, or no, I don't need cooling. And then that returns to the chill water plant. So this is where all of your energy in pumps and the cooling piece of the pie is being used. So we're cooling Betty, but what about in the middle of winter and addressing our big piece of the pie? We need to heat also. So heating in a classic building design comes from your boilers. So we've got a boiler plant, which typically makes steam converted to hot water. So in your boiler plant, natural gas fired likely, we're converting that to water, and then we're pumping that into the building. And when we talked about this VAV box, that's what's controlling airflow to Betty's office. But in that VAV box is a little heating coil. So if it gets too cold in there, that's where Betty gets the heat. That's also controlled by her thermostat. So in all the VAV boxes, in every space in your building, there's a heating coil. And then there's also a heating coil up here in the air handling unit with a controller. So these are very technical, right? So we're laying the groundwork here. These are your mechanical systems. It's important to understand how they relate and how they provide cooling and thermal comfort to the building. And perhaps the most important piece of this is the brains behind it. These are all controlled by a computer. I'm sure all the building operators and facility managers have a building automation system. Who has logged into their building automation system in the last week? Okay, a couple of you. So what you may or may not know is that all the mechanical systems in the building, this VAV box supplying this room, the maintenance guy can log into a computer and see this VAV box. He can see exactly what our temperature is. He can see what the discharge air temperature is out of that diffuser. He can see what this damper position is. He can see what the sort of heating coil valve position is. He can see all of those things because all of this is computerized. So in the air handler, there's a panel. There's a control panel. And that control panel controls this chill water valve, controls the hot water valve, it controls this damper that's bringing in outside air, controls the fan speed, also probably reads the temperature coming out of this air handler. So, and a lot more points, but that's the gist of it. And so this controller talks back to your central PC, and this is where your maintenance staff, this is the guy in the, this is where your maintenance staff manages all of the systems in your building. So this is called the building automation system. Keyword, automation. So if this building automation system is optimized, all of these mechanical systems, then your building is running efficiently. And if it's not, we'll go find it and fix it. So that kind of lays the groundwork on building systems and building structure. And now I'll talk a little bit about what we do with all this and how we find energy savings in these systems. So top 10 energy savers, David Letterman style. I'm going to run through them real quick, and then we'll talk about each one, and then I'll show you some real building applications where we've identified savings, we've actually implemented projects. I'll show you the before and after with a bunch of nerdy graphs. But number 10, do you have closed balancing valves on variable flow systems? One of the things that I didn't talk about is these pumps are likely controlled by a device that we call a VFD. It's a variable frequency drive. It controls the speed of the pump. So basically, you don't need full-on cooling all year. March, you may need a little bit of cooling. July, you need a lot of cooling. But this pump can respond to that load, and the VFD can control the speed. So if we're controlling the speed of that pump, we don't need to be throttling back the water flow in a pipe. And I'll show you an application of that. Number 9, tune your boilers. Our biggest energy user in the building is your boiler. We should tune them at least once a year. And insulating steam pipes is a total no-brainer. Pays for itself a year, if that. Do your VAV box settings meet or exceed code requirements? This is a little techie one, and we'll talk about the details of that. Can you use occupancy sensors? Most people think of an occupancy sensor as a lighting control device, but we actually use it to control ventilation in spaces. We can use that occupancy sensor. If Betty goes home, we can use that occupancy sensor to control the settings of her VAV box. Go inspect 1AHU. Go stay on your roof and look at one of your air handlers. We'll talk about what the economizer is. What's your chiller plant delta T? That's a really good one. It's sort of hard to diagnose why your delta T might not be just right, but it's an ideal question to ask to identify to water plant performance. Can you schedule equipment? Is your building 24/7? Does everyone go home at night? Is there some opportunity to shut back these systems because the people aren't in the building to need them? Do you have really ancient pneumatic controls? And if you do, you probably really want to get rid of them. Oh, and the worst thing is, have you abandoned the building automation system? We really are looking for automation here. If it's an operator override, that means somebody has they've overridden the automation and now your system is no longer working so that it's responding to its load according to the computer programming. It's just doing whatever someone put the set point at. So we want to look for those. And then the number one thing you can do, or should do, the first thing you should do in your building to manage energy is what? What do you think? You've got this building, kind of want to know how it's performing, you're looking for energy savings. What do you do first? Audit. Look at your utility bills. How much gas am I using? Audit would address that. Measure it. Measure it. What do my gas bills say I'm using, and what do my electric bills say I'm using? What is your building energy performance? Okay, so now we'll dig into each one of those a little bit. Building energy performance. So, is everybody familiar with Energy Star? You probably have that on your TV or your PC, maybe your laptop. So Energy Star is created by the EPA. They have an online portfolio manager. You can input your building into the portfolio manager, and it evaluates your building. You get a score based on how your peer buildings perform. So EPA created an algorithm based on CBEX data years ago, and that's kind of what they use as the structure, as a giant database out there that creates the structure that evaluates the location of your building. So what climate are you dealing with? What type of building activity do you have? Is it healthcare? Is it higher education? Is it office building? What's your square footage? And then a few other metrics determine it depending on what type of building it is. And it gives you a score. So if your score is 0 to 100, 100 is your best performer. And if you were to put your building utility bills in there, you put your gas bills and electric bills in. That's pretty much it. Pretty straightforward. And you put your building in there and you get a 6. So what do? You talk to your manager and say, we have some energy issues to deal with here. We actually had that experience, and I'll show you some examples of what we did in a building that we found to be a 6. But this is a great place to start. 85% of the healthcare building stock in the United States uses Portfolio Manager. So, yeah, it's super simple. You know, it's not uber rigorous, but it lands you in the ballpark. Am I a 6 or am I a 90? And if you're a 90, then you should get recognition for it, and you should apply for the Energy Star Award. So Energy Star Portfolio Manager. Okay, so now we'll get a little nerdier and talk about trends. So one of the other things we can do to measure is we use this building automation system, and maybe many of you do this already, but we can set up trends in this building automation system, and remember, it's looking at all of the details of how this air handler is running. It's looking at your fan speed, it's looking at your chill water valve position, it's looking at your hot water valve position, your outside air damper, and what temperature it's delivering out to the building. So we can trend those. We can program this to say, every 15 minutes, I want you to capture that information. And then it stores it, and then we can plot it on a time series, which is what you see here. So this is time series data from, this is from an air handler in Kaja in Idaho. And you can definitely tell already there's some before and after data going on there. The before data is from March. And again, this is 15-minute data, but it's March 4th. So we're seeing about a day and a half's worth of data. And so what we do when we try to figure out, are these mechanical systems working right? Well, you can go look at them in the field and maybe determine a few things. But what are they doing over time? What did they do last night? Did they modulate back like they should because the load was less? Well, in this case, we're looking at the economizer on this air handling unit. And the economizer is kind of another word for this outside air damper. And one of the things we didn't talk about quite yet is the job of this air handling unit is to deliver 55-degree air to the space. So this is meant to be 55 degrees all the time, unless you're doing a reset, which is great. So the job of this air handler is to deliver 55 degrees. And if it's 55 degrees outside, what would we want to have happen here? We want the outside air damper to be fully open, right? So if this is supposed to make 55 degrees, that's the cheapest way to get there, but it's the free way to get there. It's bring in all the air from outside. Don't take any of the return airs 70 degrees. We don't want 70-degree air, we want the outside air 55 degrees. So that's what we call the economizer. It's free cooling, basically. So when we run trends on this air handler, we're seeing that the outside air damper is at 20%. Not ideal, right? So we take a look at the control system to see what was happening. We found out it was an operator override. Somebody told it to be 20%, and they left it there. So we freed it. And we freed it on March 5th at 10 a.m. And you can see what happened. The outside air damper totally opened. Now all of a sudden we're getting this 55-degree air from outside the way we're supposed to. You're like, okay, well that's great. The airflow is coming from the right place. What does that mean energy-wise? So this is what it means energy-wise. The blue line is the position of this chill water valve. So the chill water valve was open. And the chill water valve, this is a chill water coil in the air handler. That's what's providing cooling in the air handler. The chill water valve is open 60 to 80%. So we're using mechanical cooling. We're using chill water to make the 55-degree air. We're running a pump back here to get the chill water out there. We're running the chillers, all to make this 55-degree air because this damper was in the wrong position. So when we freed the damper, now all of a sudden we're getting the air from outside like we're supposed to be. And you can see what happened to the chill water valve. Totally closed because we didn't need it anymore. So this valve closes. If this were the only air handler in the system, this pump would no longer be running and the chiller would no longer be running. And now we're getting free cooling. So this is an example of why we measure it. We use trends a lot in the building automation system to measure. Anybody have any questions? Okay. Number two, this kind of follows on the heels of number one, and it kind of gives you a visual for a building automation system screen. So if you're the building operator and you log into your BAS, have a look at what's happening with this air handler, this is what you see. There's a little bit more detail on this particular one. But there's our supply fan. It's supplying air, in this case to the auditorium. The set point is 55 degrees. There's our chill water coil, there's our hot water coil. We can see what the valve percentages are. Here is our outside air damper. So this would be our economizer. Here's our return air damper. In this case, they've got return air fans, which I didn't draw on here, but so you can see this has a set point. And one of the things we look for are operator overrides, like I talked about. There's varying degrees of override and varying degrees of severity. This first one we call minor infraction because it's really not that bad, but it's still not great. So what can happen is Betty calls in the middle of the night, not the middle of the night, Betty calls in the late evening and the night operator is on staff and she's hot. So the night operator says, oh geez, Betty's pretty important at this organization, so he resets this discharge air temperature to 50 because Betty's hot, and if you send colder air out there, it's probably going to fix it, right? So now Betty's getting colder air and presumably she's satisfied. And then that set point remains in place for weeks if no one goes to look. So if you're sending 50-degree air into the building instead of 55-degree air, you can imagine how many of these heating coils are going to be engaged all over your building to warm that air back up before it delivers it into the spaces. So in that case, really what we want to do is go figure out why Betty's hot, what's going on with her particular PAD box, and fix that instead of overriding a temperature set point at the air handler. So those are things to look for because they have great energy implications and they're totally easy to fix. But this is a minor infraction, not a super big problem. The other option, which is a little bit more tragic, and this is a misdemeanor, no more serious. The night operator says Betty's hot. What am I going to do about that? Well, let's see. She needs more cooling, so I'm going to take this chill water valve and I'm going to command it to 100% because she needs more cooling. And I'm not making this up. It sounds ridiculous, doesn't it? And it's not really a story, but there's been a couple of buildings we've worked in where they're trying to get more cooling into the building, so they command the chill water valve to 100%. So granted, that probably makes Betty's office colder. But what also happens if you run trends and you look at the air handler at night, when load drops off, then all of a sudden there's so much cooling going into this air handler because this is commanded to 100%. But the heating comes on, we see the heating come on at night. So, so commanding devices like that has incredible energy implication. So one of the first things we do is run a points list in a building automation system, and you can see what mode every point in your entire building automation system is in. So you can see if it's an automatic mode or you can see if it's an operator override. And then you can go investigate why those are where they are. So operator overrides, bad, but you can find these. You can run a report in your building automation system. I'd say every once a month you should run a report in your building automation system and find out what's an operator override. This is another way to override. I'll kind of skip this, but basically you can override at this little field panel right here. You can still see that that's happened in your automation system, so not ideal, but identifiable. And then the worst one. This one's a felony because you cannot run a report in your building automation system and see this one. Who knows what an HOA switch is? Hand off auto, yes. So on your rotating equipment, for example, this pump right here, in addition to speed control, it has we call it HOA switch, hand off auto. And this is a field switch. So this is designed for the guy in the field. He wants to test this pump. Maybe he's doing some diagnostics or something on this pump. He wants to force it to run, so he puts it in hand. Basically, he's taken it out of automatic. If the pump's in automatic, then the BAS is telling it what to do, and that's ideal. That's what we want, because then it can respond to building load and it can modulate. But if it's in hand, then it's going to run full on all the time. There's an off option so that a building operator can turn the pump off and do whatever he needs to do with his field work. So if this pump is in hand, you cannot see that in the building automation system. You'll probably see some identifier. We've had a number of these kind of things happen. We're like, how's this space getting all this air? The unit is off. And then we walk out to the field and the fan control's in hand. And it had been in hand for months because the guy worked on it a couple months ago. So super simple. Walk your, you find this on your motor control centers, your MCC. So go walk your motor control centers. Are all of my HOA switches in auto? That's where you want them. That's a felony. I did this presentation to a BYU student class, and I was talking about this minor infraction and a misdemeanor, and it's kind of supposed to be funny. And there was this fidgety guy in the back, and he raises his hand and he goes, "Is it really a felony?" So these are undetectable in your control system, can't see it on the graphics. Okay, does anybody have these in their building? Oh. So these are pneumatic controls. They're controlled by air pressure, basically. They're ancient, and in some ways they're kind of darling. My dad used to be an HVAC maintenance guy, and when I go home at Christmas and we talk about building controls, he's like, "Oh, Jane, I can do anything with pneumatics." Which I'm sure he could. But if you have pneumatics in your building, they're probably very old, they probably aren't working right. You should be budgeting to replace those. You can't see any of those. When I talk about pneumatics, those are not, what that means is, if this BAV box is pneumatic, then it's being controlled by air pressure and a local thermostat. There's no visibility at your building automation system as to what's going on at this piece of equipment. And there are some facilities that have entire air handlers, big, 100 horsepower air handlers running on pneumatic controls. So there's a lot of energy opportunity savings there. And here's an example. So this also is from a hospital in Kaja. So again, we go to this hospital and we set up trends so we can measure things and see what's going on with the systems. And what we see is that one of their air handlers, this is again time series data, this is fan speed for one of their air handlers. In April, there's quite a bit of data there, a couple weeks worth of data. In April, in Idaho, so it's not very cold. It's actually it's not very hot, yes, I'm saying. It's not very hot in Idaho in April, so I would not expect the fan to be pegged. This fan was on a variable frequency drive, so it should have been slowing down and speeding up, responding to space load, but it's not. It's pretty much up there at 90-some% all the time. So they had pneumatic boxes. So we could see this air handler digitally in the control system, but all of these terminal units that this air handler was supplying were pneumatic, and they were from 1984. So we can't see what's happening with them. We can't see that they're not working right. But we did a replacement project. It was time for them to do an upgrade. So they replaced all of these boxes with digital boxes that now they can see in their building automation system. And we did nothing to the fan and collected a little more data on the fan. And then you can see after, this data is from November once the project was installed. After, you can see what the fan is doing now. It has nothing to do with any changes we made with the fan. It's just that now this box damper out there, it's actually closing off the way it's supposed to respond to what the space temperature wants to be. So that's an example of replacing your pneumatics and how you can save money. This particular system, I think there were only 13 BAV boxes, so it wasn't a very big system, but they're saving $5,000 a year. between fan savings and cooling savings and reheat savings. And then the maintenance guy can actually see what's going on in the building automation system. So, really good project. Does anybody have any questions? Yeah?
How were you able to get diagnostics if it was the older pneumatic system? But how were you able to find out that it was running at 90% when it was an older system?
Oh, this is the air handler itself was in the building automation system. So the air handler was reading into the control system, so we could collect this fan speed data, and that's what you see on the graph. So the air handler was in there. It's just that the boxes weren't. So, anybody else? Yes?
So was it operating with duct static, air static?
Yes.
So
Yes.
It's just the other VAVs weren't closing all the way, and you still had to provide more air?
They're pneumatic, so what we realized is that the pneumatic boxes, the old pneumatic boxes, they just weren't working. I mean, they were old and pneumatics leak and things get tired and the dampers don't turn back anymore to create that static pressure to slow down the fan. So that's what was happening. The boxes just weren't responding out there. So once we installed the new boxes and the boxes said, my space temperature is satisfied, I can reduce the airflow, then it would build up the static pressure and then the fan would slow down. Make sense?
Yeah.
Cool. Okay, don't panic. This one's kind of busy, but it's cool. So when we talk about working in a healthcare environment, it's a 24/7 facility, right? So nothing is ever scheduled. But once you start doing a little bit more investigation and working with the staff, kind of talking about their spaces, and you realize that they have, air handling units on their admin area, or a certain clinic area, or the PT department, and all of those spaces go home at night. And they run the air handlers all the time because it's a hospital. So this is actually data from Primary Children's. We did some really cool projects with them. They were welcoming of new ideas. And it's a little bit busy, but what I want you to focus on is the gold line, and that is fan speed. So, I lost my, there we go. So this gold line is fan speed. And again, we set up trends in the building automation system. This is air handler 12 at Primary Children's. And it kind of looks like it's running right. There's nothing wrong with the fan. It's coming up a little bit more during the day because there's more load, there's more people in the space, and then at night it drops off. So we have about 5 or 6 days worth of data. Fan looks like it's good, but there's no one in there at night. So the fan doesn't really need to be running all night. So we talked to the staff about it. They were game to shut down the air handler with the qualification that if any of these spaces, and we could poll the spaces because in the building automation system we can see this temperature, because we've got digital controls, we can see the temperature of every one of the spaces. If we poll them all, and any one of them gets out of their criteria, the air handling unit comes back on. So that seems okay, right? What we don't want to do, we've totally stayed away from scheduling, meaning that you let the space go down to 60 and up to 80. Because invariably, somebody will come in the middle of the night and they're like, my office is 80 degrees, who did that? And they file a complaint, they're an important doctor, and then the scheduling gets pulled and you never get to schedule and you can zip your building ever again. So we take the conservative road, control the space at night between 69 and 74, but let the airflow to the space turn off as long as the temperature is satisfied. So that's kind of exactly what happened when we put the program in place. You can see the air handler, it's kind of cool, you can tell it's working. The air handler turns off, so the gold line goes down to 0, air handler's off, a little bit of time goes by, and the air handler comes back on because one of these spaces was out of temperature range, brought it back into range, and then throughout the whole rest of the night, the air handler's off. So we've got hours here from 18 o'clock to 7 o'clock in the morning. This fan, 100 horsepower fan, is off. and space temperature is still reasonable. If anyone were to come into those spaces, the space temperature is still reasonable, they would have really no idea that their air handler is off. And it's I should qualify that code, especially in a healthcare environment, drives everything. Patient comfort is primary. Any of the energy measures that we propose or put into place are, they meet code requirements. We never reduce airflow when it's not a code legitimate situation. So the other cool thing that happened here is, this is the purple line. The purple line's got some issues, right? Aside from the fact that we should be scheduling this air handler, the purple line is the chill water valve. And it's going back and forth. Again, this is 15-minute data, so we've got some issues here with the chill water valve. But what happens to the chill water valve when the air handler goes off? It's closed. So air handler goes off, we have fan savings. Chill water valve closes, we no longer need to pump water there or create chill water at the chiller. So electric energy savings in the fan, and then cooling savings at the chiller plant. Questions? Okay, speaking of the chiller plant, this is probably my most favorite slide of my entire career, so I'm glad to get to share it with you guys. So this is a chiller plant at Intermountain Medical Center, which you know is it's the largest hospital in the state of Utah. It's Intermountain Healthcare's flagship building. I don't see any Intermountain Healthcare people here, do I? It's a great building. It was built in 2007, great design, and we went and did an energy audit in 2009, so it had been operating for a couple of years, and their Energy Star score was 6. 6. So fresh out of the wrapper, brand new building, 6. So we sent out trends. What's going on? What's going on with our mechanical systems? Let's go look at the chill water plant and see what's happening out here. These are big, giant energy users. They have an 8,000-ton chill water plant. So really, really big plant. So we ran trends, and let's talk about a little bit for a second about how a chill water plant is meant to work. This chiller, its job is to make 44-degree water, classically. So this is making 44-degree water, and in the case of Intermountain Medical Center, it's pumping this water through 24-inch diameter pipes all across the campus, and the campus is probably, you guys have seen it, half a mile, 3/4 of a mile long. So this is a big system. We're pumping a lot of water along the way. So we're making 44-degree water, and we're sending it to the air handler, and then it's coming back. And imagine if it comes back at 45 degrees. So you send it out at 44, and then if it comes back at 45, like what happened? Nothing really. That's the problem. It didn't do any cooling. It didn't do its job. We sent a lot of water out there, and then it didn't transfer any heat. So what we're looking for in chill water plant performance is send 44-degree water out there, and you want it to come back at 54 degrees. We want a delta T. What's a delta? We want a delta T. If we're going to send the water out there, we want it to do its job. We want it to cool 10 degrees in the air handler and then come back to the plant. So those are the things we're looking for when I talked earlier about what is your chill water plant delta T. You should go look at your chill water plant delta T. If it's 3, then you're moving too much water and it's not doing its job when it's out there. So we can see that happening in this early data that was collected. The blue line is the flow. So here's our flow. So this is before we did any work. This is how the plant had been running since 2007. So this data is actually from 2010. So it came online in 2007. We collected this data in 2010. And here's our flow. Flow is actually measured on this axis, so it's bobbing around between 4,000 GPM and 8,000 GPM, sending tons of water to the campus. And then we look at chill water supply temperatures, the green line, and it's on this axis over here. So it's way up there. That's not 44. We're up here between 50 and 60 degrees. And then the return water is the red line, temperature. So what we're going to look at is the difference between the red line and the green line. That's our delta T. That's what tells us that the chilled water is doing its job when it's out on the campus. And they're pretty super close. They were at about a 3 to 4 degree delta T. So again, like brand new system, they had a great building automation system. They had really good equipment. It just wasn't sequenced right. So we reprogrammed the pumps so that they responded to building load instead of being sequenced the way they were originally. We resequenced the chillers so that they were optimized based on their best efficiency point. And then we controlled the water temperature so that we were maintaining this 10 degree delta T. And then we collected a little more data afterwards. And you can see this is from September. So September is a lot hotter than March. And our September data from the chill water flow, oh, look at that, sweet. Now we're floating around here between 3,000 and 4,000 GPM, getting pumped all the way across this campus. And we've got a daily cycle. So during the day, you need more cooling. At night, it backs off. Our chill water flow is completely responding to the load in the building. And I bet that's the weekend. I'd be curious to look that up. September 7th, that's probably the weekend, because things are being shut off. So now we've totally controlled the flow, and then you can see the chill water delta T, we're delivering 44 degree water, and it's coming back, having done its job. So really great project. We did buy some VFDs for the condenser water pumps, but basically they didn't have to buy anything to make this project happen. They really just needed to build the right intelligence and the right sequence of operation into the program that they had. $78,000 a year savings from this project. Totally great project. Do I have any questions about that? Yes?
I guess I'm just thinking, good story, but it's a bad story that they've been wasting $78,000 a year. Who's responsible for that initial proper sequencing? And why can't building owners be assured that when they turn the key, open the door in a new building, that's taken care of? I imagine it was a commissioned project.
Yeah, that's a good point. I don't know if everybody can hear that, but there's a slight berating for the fact that they were spending $78,000 a year from 2007 that they didn't need to. And the takeaway from that is that Intermountain Healthcare was acknowledged that, and they said, oh my gosh, we're building buildings that we're not commissioning. We're not making sure the systems are working right. And they've made that change in their process. So now, when they bring a new building online, it's commissioned. Like Salt Lake Clinic that you've probably seen on 4 South, that building was completely commissioned, really successful building. There are no pieces of equipment running in that building like we're seeing here. So that deficiency has been identified, and as an organization, they're correcting that. And the idea is to get that message to as many people who are building a building as possible. Sorry.
So, the total energy expenditure, what percentage is the $78,000?
They reduced their electric energy use by 12%. I'll show you that at the end. And again, this is a giant campus, so there's a lot to do. This was a big piece of it. But we'll show you. I'll actually have a graph of their energy use at the end. I'll share that with you. Is there another question somewhere? Yeah.
You said change the water temperature. So what? You can't just change the water temperature. You have to send it out at 44. So we say change the water temperature. What specifically was done to do that? Was the modulation?
Well, what we really did, and this is a little bit more complicated system than I drew up here. It's a primary secondary pumping system. If you're familiar with primary secondary heating, yeah, maybe we should talk later. They actually have this in their pumping configuration. They have a primary pump which is dedicated to a chiller. That pump's job is to make sure water flows through the chiller. And then off of that, they actually have a second set of pumps called their secondary pumps. And those secondary pumps are what pull off of this primary loop to deliver water to the building. And what happens is, and then there's a bypass in there. So it gets a little techier, but what happens is you end up circulating water through the building back to the building itself instead of getting the water out of the chiller. And maybe we can talk about that later with a little better diagram. But it's really about controlling these pumps that are delivering the water to the building based on the load instead of sequencing chillers on in different fashion. So, anybody else? How's my time? Do I have a time check? Oh my gosh, look. Oh my god, it's almost lunch. We have 10 minutes. Let me, let's see. Let's talk through this one, and then I'll let you guys go. So this is an air handler. You can already see a few things wrong there, right? So this is an air handler at Primary Children's, and again, we ran trends in the building automation system to see what was going on with it. And these are some things you should look for, like how are your devices on your air handler performing? If you went and stood next to this air handler, you would watch that damper open and then close. So this damper, you could stand there literally and watch it. We did. Open and close over maybe 2 or 3 minutes, maybe 5 minutes. It would cycle totally open and it would cycle totally closed. And the worst part of that, well, actually, we'll talk through how we fix that. So we've got this damper cycling. And really all that is a control loop. The programming control loop for that damper just needs to be slowed down. It's basically responding too quickly to what was controlling it. It's kind of a simple fix. So we fixed it. The controls contractor fixed it. We said, can you fix that? And they fixed it. And you can see that they fixed it here, because now the damper, oh my gosh, so much better, right? So now the damper is opening and closing once a day, kind of responding to the outside air temperature. That's your air side economizer, responding to outside air temperature, perfect. So now it's got this nice profile. And the other thing that was happening that totally got fixed as a result is the blue line in there is a chill water valve. So we have this outside air damper going back and forth. And if you remember, this air handler's job is to deliver 55-degree air. So that's its job. And so it's going to control the devices within to do that. But this outside air damper is opening and closing and setting completely variable temperatures into the coils. So it's like, oh my gosh, it's too hot. I need some chill water. So it turns on the chill water valve. And it's like, oh my gosh, it's freezing in here. So it turns on the heating coil. So you've got this complete response happening, which you can see on the graph. The blue line is chill water valve, cycling back and forth from closed to 40%. Then the red line is the heating valve, cycling on and off. So tragic, right? Tragic. And the whole time, it's 40 degrees outside. The purple line on the graph is 40 degrees, and it's kind of floating around 40 degrees. Basically means that this air handler can deliver 55 degrees in the building without using heating or cooling. All it needs to do is mix the 40-degree outside air with our 70-degree return air, and it shouldn't need heating or cooling the whole time, but we were using both. So by fixing that damper control, totally settled out the whole operation of the unit. Again, great project. $28,000 a year. They were just using a ton of heating and cooling, and then your devices are out there cycling back and forth. Like, those are things you want to identify. That's definitely going to affect the life of your devices. So I will skip ahead through a bunch of these. Use occupancy sensors. Check your VFD boxes. Tune your boilers. Don't restrict flow in your pumps if you've got a VFD on the pump. In this particular case, they had VFDs on this pump. There's VFD can control the speed of the pump, and yet we were restricting flow to meet design. So we opened up this valve 35 feet ahead. We opened up this valve and then just slowed the pump down, and the system totally did the exact same thing we wanted. Really great savings, super cheap. But to answer your question, This is what happened at Intermountain Medical Center. These are actual utility bills. So this is use. We're looking at use, not cost, because rates vary, right? We don't want to look at that. We want to look at how much less energy is the building using. When they came online in 2008, they're kind of still getting up to speed, but you can see in 2009, they're on the incline. Blue is electric, red is gas. We did an audit with them in 2009 and then started some of the projects that I shared with you. And originally, their expense was $4.3 million, 12% electric reduction so far. This is as of 2011. They've continued to do a number of projects since then, and they still are. Great gas reduction. They're saving $500,000 a year in the whole facility as of these measurements. So this is why we do this. I won't keep you any longer. We're limited, so if anyone has any questions, appreciate your time and letting me share of our nerdy experiences with you. Anybody have questions?